So good evening. I'm delighted to welcome you all to the third event in the Meet the Researchers Achieving Net Zero webinar series. The series has been developed by the Alumni and Development team in partnership with the university's Priestley International Centre for Climate Change. My name is Rachel Spraggs and I'll be chairing the webinar today. I actually have a personal interest in this subject as I co-lead our Institute of Applied Geoscience and I'm playing an active role in developing new research projects to deliver our low carbon transition. I'm also a Leeds alum, so I feel like I'm in good company this evening. In 2019, the UK government introduced groundbreaking legislation to reduce greenhouse gas emissions to net zero by 2050. This was informed by net zero recommendations from the Climate Change Committee, and these recommendations were underpinned by a wealth of research from the University of Leeds academics. Since then, we have witnessed a wave of net zero commitments from nations, cities, businesses, and investors. The University of Leeds itself announced ambitious commitments to reduce its own carbon footprint to net zero by 2030 and focus its teaching, research, and engagement on addressing the grand challenge of climate change. Our net zero research spans three key areas of action: decarbonising our energy supply, reducing our demands for energy services, and the capture and removal of emissions. Researchers are also focused on three cross-cutting fundamental principles: ensuring a just transition, resilience to the impacts of a changing climate, and delivering multiple co-benefits. The researchers contributing to this series will offer an excellent insight into some of the important work that's underway at the University of Leeds. So just before I introduce our speaker this evening, I'd just like to explain how the webinar works. There will be plenty of time for questions at the end of the presentation. And if you look on your screens, you should see a Q&A function at the bottom. You can upload your questions at any time, so don't feel like you have to wait until the end. And if somebody else asks a question that you like the look of, feel free to upvote the question, which means it will appear higher up my list of questions and I will be able to ask those questions of our speaker at the end. The last thing I have to mention is that the webinar is being recorded. So if anybody needs to leave early, that's fine. You'll be able to catch up on the bits that you missed later. So today I'm delighted to welcome my colleague, Professor Chris Rayner, who will be talking about using carbon capture to clean up industry. Chris is Professor of Organic Chemistry at Leeds from the School of Chemistry and also founder director of C-Capture. Right, over to you, Chris.
Thank you very much, Rachel. First of all, I take the opportunity to publicly congratulate you on your Women of Achievement Award from the university, well deserved. And really great to see. Okay, thanks for the introduction and the opportunity to speak today. It's wonderful to see such a broad audience from all different backgrounds and also, of course, all around the world, essentially, which is really great. I'm going to talk today about some work that originated in the chemistry department at the university, probably about sort of 10-15 years ago, something like that. I'm a synthetic organic chemist, been in the university for about 30 years, but about 20 years ago, I started working with a colleague, Tony Clifford and Keith Bartle, who some of you may have come across when you were in Leeds. And basically what we were doing was using high pressure CO2 to extract natural products from plants. In this case, it was a yew tree. We were trying to extract some anti-cancer agents, and we were using high-pressure CO2 or supercritical CO2, as we call it, to do that. And that really got me interested in CO2 chemistry. That was 20 years ago. That was old, but my interests have evolved substantially over that period of time. And what I'm going to tell you about today is a story about carbon capture and how we set up a company called C-Capture, which was basically to commercialize some chemistry that we developed that allows us to reversibly capture carbon dioxide out of gas streams. And probably when we first started doing this work, it was very early days, and certainly the environment and things like that was certainly not as high on the agenda as it is today. So there we go. Okay, so just a little bit of background to start off with. I'm sure most of you are familiar with a lot of this. But just a bit of history. So the Paris Agreement, 2015, the key thing here was to limit global warming by less than 2 degrees centigrade, and preferably nearer to 1.5 if we can. And then more recently, we've had government's commitment to net zero. This is quite an interesting development. Before net zero, it was 80% reduction in CO2 emissions compared with 1990 levels. One of the issues with the 80% reduction was, of course, everybody thought they were part of the 20%, so they didn't have to worry about this. But net zero means everybody's got to be zero. We've got to do everything we can to get the CO2 emissions essentially to zero. And this talk today is really a very good timing in that yesterday, actually, the government actually released its industrial decarbonisation strategy. And carbon capture and storage, which I'm going to tell you about, features very heavily in all of this. It's quite a long document, about 160 pages. If you can't sleep at night, it's worth having a read through because it will send you to sleep. But it's actually got a lot of stuff in there. Probably doesn't go quite as far as many people would like who are very active in the area, but it's a really good start. And you know, for somebody who's been working in this area for the last 10 or 15 years, it really does feel like there's some momentum building in this area now, which is really, really good to see. So a little bit about net zero and how we can get there. The key thing is we need to fundamentally reduce global emissions wherever possible, and we're about to embark, or we've already embarked on an unprecedented transition in how we produce, transport, and use energy. Our lives now, compared in 20 years' time, is actually going to look very different in terms of how we use energy, how we move around the UK or even around the world. And of course, there's a huge role for renewables in all of this. You know, solar power, wind power, maybe other types. But carbon capture and storage is really a key technology for decarbonisation in the UK and around the world. And it's required really to reduce emissions from sectors which are pretty hard to decarbonise. So things like cement, this is heavy industry, heavy manufacturing. So cement, for example, is an inherent problem with when you manufacture cement. It's not just heating, you actually do produce CO2 when you make cement. Iron and steel, glass and ceramics, waste to energy plants, burning waste to produce energy, chemical manufacture, for example, including oil refineries, and hydrogen production. All of these processes, these large-scale industrial processes, they all produce a lot of CO2. And basically at the moment, it's all going into the atmosphere. We've got to stop that. We've got to capture that CO2 and do something with it, store it hopefully somewhere deep underground where it'll stay for hundreds, if not thousands of years. Alongside that, we've got lots and lots of CO2 in the atmosphere, far too much of it really. And so there are things called negative emissions technologies, which are emerging. And one which I'll say a little bit about today is bioenergy with CCS, where you're actually burning wood or wood chips, and you're capturing the CO2 that comes from that. And this has a potential to be what's called a negative emissions technologies, where you're removing the CO2 out of the atmosphere and essentially storing it back underground. And most pathways that limit global warming to 1.5 degrees centigrade really rely on large-scale deployment of BECCS alongside other negative emissions technologies, particularly afforestation, or planting lots of trees. There's also something called direct air capture as well. But all of these things are going to be required, particularly if we're going to carry on using aviation, for example. Aviation is one of the industries. It's actually very, very difficult to decarbonise, and so to get to net zero, we're going to have to do some negative emissions to actually cancel all of that out. So I'm aware we've got quite a broad audience, so I'm going to try and keep this reasonably simple. This is how we do carbon dioxide capture. So we'll typically have a feed gas stream. So this is a gas stream, maybe at the back end of a power station or a back end of an industrial process, maybe a blast furnace, and that needs cooling down. And then we pass it through a process, some sort of chemical process. And what you'll see is you get one stream of carbon dioxide. So we've separated out of the carbon dioxide essentially from everything else. So we get two streams, one of which is carbon dioxide, the other of which is everything else. And how do we do this? Well, what we have is a chemical which reacts selectively with CO2 to capture it, leaves all the other gases in what is an absorber to go through the absorber. And then what you want is for that CO2 reaction to be reversible so that you can regenerate your absorbent and get your pure CO2. So the process relies on CO2 reacting selectively and reversibly in a chemical process where other gases, particularly things like oxygen, don't. They pass straight through your chemical process. So that's the basics. This is perhaps a little bit more detailed of how this would work. And so what I've got here, for example, is this is just an industrial gas stream. It looks a bit like a power station. I guess it is. You've got cooling towers there. So this is power station. And from that power station, you have a flue gas. And typically, if it's coal-fired, it'll be about 15% CO2. If it's gas-fired, it'll be 4 or 5% CO2. So you have to tweak your process depending on the levels of CO2 in there. And that flue gas then is blown up from the bottom of this absorber column here. And this is typically around 30 to 40 degrees centigrade, something like that. And basically what you've got is a solvent that rains down. So you spray your solvent down this absorber, it trickles down, and slowly coming down. As it comes down, what it does, it picks up CO2 selectively and drags the CO2 down with it. But anything else that doesn't react with your solvent actually carries on going up and eventually comes out the top here in this CO2 depleted flue gas. So your solvent has now got the CO2, it's been moving down, and when it gets to the bottom, essentially the solvent is what we say is fully loaded, and then we transfer that solvent, you just pump it round through a heat exchanger into what we call a stripper unit, and this is at much higher temperature. This is typically about 100, 120 degrees centigrade here. And at those sorts of temperatures, what happens is the CO2 becomes dissociated from the solvent. It comes off, and so as it falls down the stripper unit, it gets hotter and hotter, the CO2 comes off and rises, and then it goes off here, whereas your solvent actually carries on falling down, and eventually when it gets to the bottom, essentially you've got your lean solvent where all the CO2's come off, but it'll be very, very hot down there, and then you can actually put that back around the process here. The hot lean solvent actually goes through the heat exchanger and pre-warms the cool loaded solvent before it goes into the stripper. So heat integration here, actually controlling the energy balance, controlling the heat, is actually very, very important for this process, just to minimize the amount of energy used. And of course, that heat has to come from somewhere. If you're heating a large stripper like this up to 120, that you need a lot of energy to do that, and that will come, in this case, it would come from a power station boiler, for example. So this heat here that we require, we call this a parasitic load. And so this is the extra energy you require to actually capture the CO2 in this kind of process. And then when you've got your CO2, what you do is you need to compress it, and typically up to about 100 bar, so 100 times atmospheric pressure. So it then occupies a much smaller volume, and then it can be sent off for transportation and storage. And so just to give you an idea of what this looks like in practice, this is a coal-fired power station actually in the US, in Houston, in Texas, that I was fortunate to visit a couple of years ago now. You can see the weather wasn't exactly that welcoming, but it was a very, very interesting visit. And so one of the key things here is this is a power station that has an amine-based carbon capture process built on it. And so these are the boilers here. And basically on one of the boilers, what they've got is a CCS plant. And so this is an absorber. So it's actually just a very long tower, and your solvent comes in the top, trickles down, and by the time it gets to the bottom, it's picked up all the CO2 in the flue gas, and then that then goes into the stripper column here, this shiny stainless steel stripper column. This is obviously at much higher temperatures, it's smaller, and it's been much more thoroughly insulated so that you don't lose any of the heat unnecessarily. And so the CO2 comes off the top here, and then you'll see here, this is where it goes. So this is the CO2 pipeline that comes from, so it's a relatively small pipeline compared with the size of the stripper. You can see, you start to get an idea of the scale of things here. And that CO2 actually goes down into pipeline, and it's actually pumped about 80 miles off from where it's captured to a depleted oil field where it's pumped down to actually help you get more oil out of the ground, as you would do in Texas. That's not a long-term sustainable use for the CO2, but it is actually one of the ways to make it pay the bills at the moment. So that's how people are actually funding this, to actually be able to build this kind of kit. This particular process actually captures around 1 million tons of CO2 every year. So that's quite a lot of CO2. But in the grand scheme of things, probably we need to be capturing tens, if not hundreds, if not thousands of tons of CO2 around the world if we're really going to reach net zero by 2050. I should say this 1 million tons. The UK's decarbonisation strategy that was released yesterday, they're proposing that by 2030 we'll actually be capturing around 3 million tons within the UK. So that's roughly about 3 of these kinds of large capture plants in the UK by the end of the decade, which is quite a challenge. These things are pretty complex to build. They're quite expensive, and so that's a reasonable start, I think, in terms of what is planned for the future. And so then, once you've captured your CO2, as I said, in the US, well, at least in Texas, what they were doing was using it for enhanced oil recovery. So what you're doing is you're pushing your CO2 down here underground, and that's pushing oil back out. So it's a useful thing you can do with CO2, but certainly in the long term, it's not sustainable, and so it's sort of a temporary measure, if you like. And certainly, as I say, helps pay the bills to actually develop the technology. But there are other places you can store the CO2, so you can pump it down into saline formations or into unminable coal seams, for example. But in the UK, what we're probably going to do mostly is actually put it down depleted oil and gas reservoirs off the North Sea. So there'll be a CO2 pipeline that runs along the, most likely the east coast of the UK, and the CO2 then will be pumped up into the depleted oil wells off there. The CO2 will stay there for hundreds, if not thousands of years. It is over 1 kilometre down. It's a long way down. As Rachel alluded to, that one of the key things here is geology, understanding the rock formations here and making sure that they are permanent there and that the CO2 will stay there for a prolonged period of time. That's very important to this whole process. There are other things you can do with the CO2. So utilization, for example, as a chemist, I'm very interested in CO2 utilization. So can you make stuff from it? So people are trying to make polymers from it, for example, or making synthetic fuels. You can do that. One of the problems, though, is the scale with which those things would operate or that you would want to manufacture is probably an order of magnitude smaller than what you really need to capture. So we'll be storing the bulk of the CO2 in off the North Sea, for example, but we'll try and use whatever we can, maybe 5 or 10% of that stream in sort of utilization technologies. Okay, so a little bit more about C-Capture. So as Rachel said, I'm the founder director. So we started it in 2009 as a spin out from the university. And really it was to create the most energy efficient CO2 capture solutions through chemistry and engineering innovation. Sounds very grand, but for many years I've been very keen on working at the chemistry and engineering interface. Those two things are very important, particularly when you want to do large scale chemistry. Having the engineers and the chemists working together is very important. Put a picture of a couple of our C-Capture employees here. So here's Rose McCarthy, who's one of our chemists, and Fatima Bilal, one of our engineers. They're actually on site at Drax. I'll tell you a bit more about that in a second. But having the chemists and the engineers working together is actually very important for this side of things. If you're going to create solutions which are viable and actually will scale up significantly. So, when we first started the company, I put at the bottom there to play a role in saving the planet. That was a bit of a pipe dream. As an academic, we all have these grand ideas and stuff, but I never really thought we would get to the stage where we are now, where we do have some fantastic technology, probably the best in the world, I think, for actually this kind of post-combustion capture process. So it really has been a fantastic opportunity, and for somebody like me to actually see the chemistry we're developing actually being scaled up is incredibly rewarding. Okay, so why do we set up C-Capture? Well, this is the main reason. So carbon dioxide capture has been around for a long, long time. First done in the 1930s. This is the original patent for amine-based CO2 capture, which was first patented in the 1930s. So CO2 itself is an acid gas, and acids react with bases, and you get a salt, and that's the basis of the capture process. So a typical base that you would react with CO2 with is an amine, and this is one of the very first that was looked at. It's called monoethanolamine, and so here's your amine group. This is the nitrogen. This is the business end of the molecule. This is where all the chemistry happens. The group, this end, actually just keeps it in aqueous solution in water, and also reduces the volatility, so it's not as volatile as it would be otherwise. But this is the key sort of amine that people have looked at to start off with, and I'll say a little bit more about that in a little while. But that nitrogen there, that end group, that's the bit that reacts with the CO2, and that's very, very important. So this technology was developed for what we call natural gas sweetening. So when natural gas occurs in the ground, it's usually got some CO2 and hydrogen sulfide in there, and these amines will take the CO2 out, and they'll also take the hydrogen sulfide out. So what's happened now is people have taken that chemistry and they've tried to adapt it for CCS, for carbon capture and storage. Of course, it's got CO2 in there, absolutely fine. It will take the CO2 out. But one of the differences, well, the main difference is the other contents of the flue gas. So you've got impurities now. For example, if you've got coal-fired power station, there's all sorts of metals in your flue gas. A flue gas also has lots of oxygen in it. Even though you would think at the end of combustion, there's still that you've got rid of all the oxygen. No, there's still a lot of oxygen in there, and amines are notoriously reactive with oxygen over a prolonged period of time. And so what happens is you get degradation of your amine just by reaction of oxygen in the absorber. And the other key thing is scale. Although natural gas sweetening is done on a large scale, the scale of the CO2 capture plants for CCS is going to be enormous, and so that is also an issue. So the three main challenges associated with amine-based systems are energy use, so that's the parasitic load, the steam that comes from the power station; degradation, that's the amine getting oxidized or undergoing thermal degradation; and also in the environment. Some amines, not all of them, some amines are particularly hazardous, and so you need to be really careful when you work with them. They can be used, but you have to be quite careful how you do it. So we looked at this and we thought there must be a better way to do it, and in particular we had a focus on trying to get an amine-free system, and that's what we did. So this chap here is Doug Barnes. He's the head of chemistry now at C-Capture. I'm proud to say he's also an alumnus of the university. He did his first degree in chemistry, and he also did his PhD with me, so I know him very well. And he's the chap really that did the vast majority of the chemistry discovery work to get our new solvent. And this is Rose McCarthy, one of our other chemists. And although I can't tell you what the content of the solvent is, this is actually it. So you can actually say you've seen it. Yeah. So this is our solvent, a sample of it, and so it is confidential, unfortunately, the actual composition, but it doesn't have any amines in there. It's amine-free. It has just carbon, hydrogen, and oxygen essentially. So it's very different to the current process. And actually having that amine-free system, it just changes all the other factors around its use as a CCS solvent. It's a solvent that's been specifically designed for CCS rather than one that was designed originally for natural gas sweetening, but then adapted for CCS. And so, for example, the energy penalty, the degradation, and the toxicity, all those things have been essentially engineered to well, I'd like to say engineered out, but certainly to minimal levels. We still have to use energy, unfortunately, but engineer it out as much as you possibly can. And so to give you a feel for that, this energy use, the parasitic load, this tells you what it is. So steam use here on the axis here. Steam use, that's how much steam you have to take from the power station or wherever it is to actually do the capture process. And this is in gigajoules per ton of CO2. So gigajoules, a joule is a unit of energy. Giga just means lots and lots of energy. And per ton, that means for every ton of CO2, this is the number of gigajoules of energy you need. And so for monoethanolamine, that's the amine I showed you early on. That uses around 3.7 gigajoules of steam per ton of CO2. For amine blends, so people have moved things on from MEA. So what they've been doing is using mixtures of amines, so 2 amines, usually one that'll give you really good kinetics and one that'll give you good loading. And those typically will use around 2.8 gigajoules per ton of CO2. Currently, our solvent is around 1.8, 1.9 gigajoules per ton, and we think we can actually probably get it lower than that. But that's a reasonable estimate, we think, a realistic estimate of what we can achieve when we do our capture process on scale. And also, perhaps, say a little bit about a solvent lifetime. So we have had a demonstrator on Drax for quite some time, and this just shows you a little bit about performance and how it changes over time. So this red line here at the bottom is fresh solvent, so it's virgin solvent that hasn't been used before, and this line above it is actually the solvent that's been aged for 6 weeks, exposed to Drax is flue gas. And so you can see this is the rate of CO2 capture here, and the CO2 loading. Usually the rate will drop as your loading increases, and that's the same for both. But you can see in this case, it's actually a little bit better when the solvent is mildly aged. Just actually works a little bit better. So you certainly don't see the normal aging effects that you often see with amines. So they do last a lot longer, and that's good in terms of just the overall cost of the process. But also it means you've got to make less chemicals, you've got to dispose of less chemicals, all sorts of advantages like that. And one of the key things for us is, we are a small company. We have 20 people, 20 employees, and so we can't do everything ourselves. And so we do work with other experts in the field. We've worked a lot with Sintef, for example, in Norway, and we've led a lot of this. Norway have been working in the CCS area for a long time. They've been capturing CO2, storing it under the North Sea for quite a long period of time now. This here diagram top right is the tiller plant. This will capture about a ton of CO2 a day when it's operating properly, and we put our solvent through that just to get verification of our energy requirements and things like that. And this thing here down the bottom here, this is the TCM, or Technology Centre Mogstad. That's the sort of next sort of scale that you would go up there. We haven't put our solvent through that process yet. We're not sure whether we will, because it's not ideal for our solvent, because our solvent is quite different to a lot of the original amines, but we made it at some stage. And so this chap here is Casper Schulderman. He's our Director of Engineering, been with the company for the last sort of 10 years, really led all the engineering aspects there. And this is Duncan Achipori, who's one of the directors at Sintef, who has been really helpful in terms of helping us get all this technology scaled up. So how do we scale it up? Well, this is basically the process. So on the left here, this is actually in a fume hood, and this is what we call a VLE apparatus, or vapor liquid equilibrium. And basically what we've got is a vessel here where we've got some solvent in, and we put some CO2 in there, and we can see how well that CO2 dissolves in the solvent at different temperatures, and we can get curves of vapor liquid equilibrium at different temperatures, so that we can see how well the CO2 dissolves in the solvent. And then when we get something interesting, we put it in a mini plant, and this will operate on sort of kilograms of CO2 per day. We'll take it then up to 100 kilograms of CO2 a day, or even a ton of CO2 a day. These two here are demonstrators that we use for biogas. This is a little bit easier to get up to those sorts of scales, mainly because there's a lot more CO2 in biogas than there is in a flue gas from, say, a power station. But it helps us develop all our technology. So just to look inside there, we've got a few people here. This is Dave Barnes, you've seen already. This is Dave Lawler at the back. Dave's a Leeds alumni also. He used to work in SPEMI as a technician, I think. This is Gergely Jacob, who did a lot of the automation for this particular rig. Here's a solvent tank here, and this is one of the absorbers there. And the stripper for this particular unit is at the back there, so you can probably just make it out, and it's covered in black foam because it's hot, and so you need to insulate it pretty well. And one of the things you get to learn as a chemist working in this sort of area is engineers really love their toys. And this is a bit of engineering that this is John McKay, one of our engineers. This is one of the things he built, his baby, along with some colleagues as well, of course. But basically, this is a 10-column absorber, and it allows us to really look at the optimum configuration for our solvent, because our solvent's a bit different to the other kinds of solvent that people use. This really allows us to look at different types of absorber mechanisms for our technology. Okay, and this perhaps is some of our most high-profile work that we've been doing. We've been working with Drax Power Station for quite some time now. Drax are also investors in the company. And basically, what we've been doing is a demonstration at around up to the 1 ton of CO2 a day sort of scale. Drax, largest power station in the UK, 4 gigawatts of electricity, roughly about 6% of the UK supply. And one of the reasons I really like this picture is that you can see that the C-Capture demonstrator here. This is in essentially a shipping container, and then we've got absorber columns that come out the top. But this unit at the back here, this great big thing here, that's actually the ducting for one of the boilers from the Drax plant. So this is where all the flue gas comes out of one of the boilers. So you can see the size of that. It's absolutely enormous. And just to give you some idea of scale, this is the inlet for the demonstrator here. The diameter of the pipe is about 10 centimeters, something like that. And we're going from there up to this sort of scale. So you can see the challenge there. And one of these boilers at Drax will produce around 10,000 tons of CO2 every day. So that's a lot of CO2. So if we're going around a ton a day up to about 10,000 tons a day, you can see there's a huge increase in scale there. That's a real challenge. 10,000 tons a day is roughly about 3.5 million tons per annum. So that's about 3 times the size of the facility at Petronova, for example. So pretty substantial. And so one of the reasons we were really keen to work with Drax is over the last 5 or 10 years, they've moved from coal to biomass. And that's potentially very, very important. They've been pretty successful there, and that allows us to address what we call negative emissions through BECCS. I mentioned this right at the beginning. So what we've been doing very successfully for the last 100 years or so is digging carbon out of the ground. So that could be coal, it could be oil, it could be natural gas, whatever, and we burn it in some sort of power station or industrial process and convert all that carbon in the ground into CO2 in the atmosphere. So we're transferring CO2 from the ground into the atmosphere. And we've done a lot of that. We've done far too much of that. BECCS sort of turns that on its head to a degree anyway. So what we've got is CO2 in the atmosphere. And of course, that CO2 in the atmosphere, with the help of a bit of sunlight, is responsible for photosynthesis. So these CO2 molecules come together to make glucose and various other things then and become trees. So we get a lot of biomass there, woody biomass. And that wood can be used for various purposes. What we probably find over the next 10, 20 years is we're going to be using a lot more wood for construction. We already do, and also for furniture, all sorts of things, of course. But when you make that wood for furniture and for construction, you also get a lot of waste. And what Drax have done is pelletize that waste, and that's what they use as their fuel. So if you can actually burn that and capture the CO2 from that burning combustion process and then pipe it underground, you can see that's the mechanism, the opposite of what we've been doing for the last 100 years. So that's a mechanism of transferring the CO2 from the atmosphere underground. And that's the basis of negative emissions. Now, there are all sorts of things you need to consider here. It's not a straightforward thing. There are CO2 emissions embedded in just, for example, harvesting the trees, transporting the wood, those sorts of things. But overall, this is net negative, and so in principle, it can help us mitigate climate change. So it's potentially very, very important. So some of the challenges, well, I think certainly for C-Capture, scale is an issue. CO production will decrease as we decarbonize, but we still produce huge amounts, millions of tons every year, and that needs to be captured, and it also needs to be stored. And we don't have much time. So to reach net zero by 2050, we really need to be rolling out deployment at scale this decade. And as you've seen, UK plans for 3 million tonnes by 2030. That's okay, but we need to do a lot better. And certainly by 2050, we need to be capturing much, much more than that, probably orders of magnitude more than that. Cost, because of the scale, these things have got to be huge. Solutions have to be inexpensive, scalable, and environmentally benign. As an academic, I'm very used to making sort of milligrams, if not grams, of material. This stuff has to be available on the ton scale, or the hundreds, if not thousands, of ton scale. So, it has to be scalable. And of course, the impact there, we've got to maximize the efficiency for CO2 removal. And if we can get negative emissions wherever we can, then that's absolutely great. So just to finish with some of the industries where we're sort of approaching, if you like, where this sort of technology can be deployed. So there's a whole range around here. So we've got steel, for example, iron and steel manufacture, BECCS, so biomass combustion, any other type of combustion as well. So gas-fired power station, for example, those, or even coal-fired in a different country. The US still uses a lot of coal. China will use a lot of coal. India uses a lot of coal. We can actually put this on those power stations if we need to. It's not our ideal use, but we can do that. Other energetic processes are glass manufacture, natural gas sweetening or upgrading, cement manufacture, got shipping, waste to energy down here, oil refining, all sorts of different energies and industries there. And at the moment, 37 billion tonnes of CO2 are emitted per annum, and at least 5,000, if not more, plants emit more than 1 million tonnes per annum of CO2. And the Global CCS Institute, which is sort of a worldwide body that looks at a lot of these things, has estimated around 2,000 CCS plants are going to need to be operational by 2040 if we're going to achieve net zero by 2050. So that's a lot of plants, 2,000. There are about 20 around the globe at the moment. So, that's a couple of orders of magnitude scale up. That's a huge challenge, but for a company like C-Capture, it's also a huge opportunity. Okay, this is an alumni meeting, so I thought I'd just give a plug for some of the people who are alumni of Leeds who have contributed to this. I mentioned Doug Barnes, our head of chemistry. He did his PhD with me in the chemistry department. Casper Schulderman is our director of engineering. He actually worked for a company called Dispersia, which was another spin-out from Leeds University. So he's sort of an alumni. I like to think of him as he is, and he's been with the company for 10 years, so I'll give him a name check anyway. Helen Atkinson did a PhD in atmospheric chemistry. Helen is our business development manager, and if any of you ever want to get in touch with C-Capture, Helen is usually the person you would deal with. Dave Lawler was in SPINI in engineering for some time as a technician, and then he now is one of our senior process operators. Lucy Bedra did an MChem in chemistry, did a final year project with me on CCS, loved the area. We had a job, and so she was very rapidly recruited there. She's a great recruit to the company. James Wheatley, James did his PhD with me also. He looked at a lot of the fundamentals of C-Capture technology after we'd sort of done the initial discoveries. Adam Al-Hossari did a degree in mechanical engineering, and he does a lot of our data analysis these days, and he's a data scientist for us. Perhaps a little bit more surprising, Richard Dennis. Richard Dennis actually had been with us for about 10 years, but Richard was a very senior person at Dewson Babcock, led their engineering and research activities for quite some time. He's now retired. He retired from C-Capture last year, but he contributed a huge amount over the years. But he did his first degree at Leeds in chemical engineering. And Shashi Bala and Guillaume Rinal, both of them did a lot of early work in the area for us, some very, very preliminary stuff, but they certainly contributed. And the next generation, Harry Oates and Oliver Stanfield, they're a couple of PhD students, great guys in my group at the moment who are working alongside the company, helping establish some of the more fundamental aspects around what we do. And there I'll go. I will finish there. I'll just thank the people who have funded a lot of this work. So IP Group are a group of venture capitalists and have had a special relationship with the university for many years, and they gave us some some funding very early on to get the company off the ground, and without them, we wouldn't be where we are. And they've kept on supporting the company for the last 10 years. Drax and BP have been with us for the last couple of years. They've been very, very supportive as well. You know, Drax have given us a lot of help in terms of accessing their site, real flue gas, all those sorts of things. BP have given us a lot of technical support as well. And we've also had a lot of funding from Bays. They've been great in helping us get things off the ground. And of course, ongoing support from the university, letting me do what I do. And also, you know, all the people that are from the university as well, all of it feeding into there. I'll just give one last plug for this chap here. This is Tom White. He's our CEO. He started with us last year and he's doing a fantastic job leading the company. And it's a very exciting time to be part of C-Capture. So I think that's the final slide. I will stop there, and I think it's back to you, Rachel.
Yep, just trying to unmute myself. Thanks, Chris. That was a really good presentation. So I'm going to kick off the question and answer session, but just before I do, I'm just going to say we're running over a little bit. So if you do need to leave at 7, don't worry. We might continue a few minutes beyond that, but obviously it'll be videoed, so you can look at the recording later.
I'm just going to turn my light on, Rachel, because it's a bit dark in here. I think the dusk has
I think we're possibly having problems with your video anyway, because I can't always see you. I can see you now. I can see your chair.
Right, sorry about that. Yes, I should have put the light on before I started.
That's fine. Okay, so we asked for people to submit questions before the webinar as well. So we're going to kick off with one of those, and then I'll move to the questions that people have asked during the talk. So can you describe the use of geosciences in achieving net zero emissions and its expertise when applied to CCS? Okay, yeah, that's a very good question. Quite predictable from yourself, I suspect. Yeah, okay. I mean, I'm not an expert in this area, but I guess historically geologists have been very good at looking for oil and gas, understanding the geology around sort of what gas fields and what makes them stable, what makes them unstable. And I think, we really need a very similar skill set for CO2 storage. We want the CO2 to be down there for hundreds, if not thousands of years, and it's very important that we understand the geology around the CO2 fields. And because of the scale that we have to do this thing on, the only place we can really store it is something that's in a great big geological feature, so like a depleted oil well, something like that. In the UK it's mainly offshore, but there's lots of onshore opportunities in I think in the likes of the USA, for example, California and stuff like that. They're talking a lot more about onshore storage rather than offshore. But all around the world, people are going to be doing CCS, and they're going to want somewhere to store the CO2. And I think it's not just CO2. I think there's probably going to be opportunities for storage of hydrogen, for example. There's a huge interest in a hydrogen economy, so using hydrogen as an energy vector. And we can make hydrogen, but it's still, we're going to need to store it. And one of the ideas, for example, I've seen project proposals where hydrogen is generated offshore using renewable energy, using wind energy, and stored in depleted gas fields offshore, and then stored until we need it, until it's at night or there's no wind or whatever, and then you can bring the hydrogen in and use that as your power source. So I think that there's real opportunities there. I think also there's a lot of interest in CO2 interactions with rocks and minerals. There's a company called Carbfix in Iceland, I think, that's been looking at mineralization of CO2 with basalt rocks. Scales at the moment are quite small, but they certainly talk about having these things at very large scales. I think a lot of this is all part of the just transition, where everybody's got certain skills and you can adapt those skills to different areas. I think probably I'm a bit of an extreme example myself. I'm a synthetic organic chemist. 30 years ago when I started as an academic, if anybody told me I'd be wandering around a power station looking at my chemistry, I think I wouldn't have believed it. So I think we all have to sort of think quite laterally at times, and how can I use my skills to really get involved in this kind of area. And there's a lot of stuff going on. There's going to be a lot of opportunities, and certainly in the next
20 to 30 years, there's going to be something of a revolution, and I think everybody should have the opportunity to play a role in that.
Okay, thank you. Well answered. So I'll kick off with a question from Dom. It seems to have gathered quite a few likes. Is there a risk that carbon capture is seen as a get out of jail free card for carbon intensive businesses to continue as usual?
There is a risk, yeah, and we certainly have to guard very carefully against that risk, and I'm very wary of that. We work a lot with BP, for example, I think one of the key things really is that we have to do everything we can, and we need to decarbonize everything as much as possible. And the public and the governments around the world have a key role in this. So oil companies won't be able to sell petrol, for example, if we're all riding bikes, if we're all on electrified public transport, if we're all bought electric cars. Oil companies aren't going to have any products to sell. So I think consumer choices there are going to guide things a lot. With governments, if you put a proper carbon price on carbon, that will certainly disincentivize people to use sort of petrochemicals, or certainly to just burn them, for example. We can use them for much more useful things. So proper carbon price, and when at the moment there are all sorts of perverse incentives. When it's cheaper to fly from Leeds to Paris as it is to take the train from Leeds to London, for example. We have to get all of those things in the right sort of order, the right sort of order of priorities, and put in a proper taking proper account of the carbon associated with those sorts of activities really needs to be done. One of the things I would say is we shouldn't alienate ourselves from the petrochemical companies. They have a huge amount to contribute here. Certainly there will be some bad actors out there, from petrochemical companies who historically have been leading climate change denial and all this sort of stuff, and we need to call them out. But the people I work with in the petrochemical industry, or at least in the energy industry, they all understand climate change. They all know what's going on. The ones I interact with, and they all want to make a difference here, and they really can. This is large-scale engineering, and that's the sort of thing that petrochemical companies really do well. And some of the people I've spoken to, they really are motivated now. A lot of them have had pretty awkward conversations over the breakfast table with their kids. What are you doing, Dad, Mum, whatever? Yeah, is this really you? And that really will motivate things. So I think what we need to really do there is engage with the willing. If people are not willing, then they will dwindle, because the tide is turning. Their companies will not exist in 10, 20 years time. So it's not going to be overnight. It's not going to happen overnight. But the likes of BP and Shell, for example, they've been under tremendous shareholder pressure to change, and I think they are changing now. Yeah, certainly everything that's happening with BP that I'm aware of at the moment, it is changing enormously. But we're not there yet. There's still a long way to go. But this is a transition, and we will be using petrochemicals, like it or not, for the next 10, 20, maybe even 30 years. Still, there's a big transition that we've got to make. We'll do it as fast as we can. But yeah, I think we just have to make sure proper rules and regulations are in place in terms of governments, and the IPCC, for example, the Climate Change Committee, all those sorts of things, overseeing all of this, making sure that everything is properly monitored. People aren't using offsets unrealistically. There's also, it could. I think historically, the last 5-10 years, carbon offsets has been a bit like the Wild West, and I think that really needs tightening up substantially around the world. And I think if we can get that right, then I think things will work out.
Thank you. Okay, so I'll move on to, I'm going to combine a couple of questions here. So one from Ben and one from Jai, hoping I've pronounced your name right. So the first part is the current main limiting factor for CCS more technology, investment, or politics focused? And how do you think it could be best addressed? And then I'm just going to add from Jai, and I can find it. What can BEIS and the government do better in its approach to CCUS delivery?
So I think one of the things that I've really noticed in the last couple of years is that the political sphere has really changed enormously, and a lot of that has come from public perception. Extinction Rebellion, all that, then Greta Thunberg and all that sort of stuff really raised the profile of climate change, and that really has motivated politicians also. And so I think there is a lot of political will now. It's still quite fragile. You've seen what happened in the US last, up until just very recently, 4 years ago. If we hadn't had a change of the administration there, we would be in a very different situation now. So I think there is an important political dimension, but it has changed for the better, I think. But also it comes down to your average person in the street, and everybody educating themselves and realizing that climate change is an issue that we all have to work together to sort it out. In terms of what BEIS can do better, I think the thing that came out of the industrial decarbonisation strategy document yesterday, I haven't read all of it. I've had a flick through. I think we need to do more, and we need to do more faster. But it will cost substantial amounts of investment to actually do that. And so putting in place all the different protocols, I think, a proper carbon price, or agreeing various business models. There's a lot of discussion on business models for CCS at the moment. Can we get good business models in place with a carbon price, contracts for difference, where maybe you're looking at power generation with and without CCS. So with CCS, you'll get a much better price, and with potentially with negative emissions, you'll get an even better price. Those sorts of things. They're being discussed out quite seriously now, and so I think a lot of that is happening, and I think a lot will be clear. Certainly, the government's trying to line everything up for the COP meeting at the end of the year, of course. Yeah, and so I think we will know a lot more this year. It really is a key year for us.
That's great, thank you. So I'm going to go back to the geology side, potentially. I've got a couple of questions here, one from Leonard and one from Dom, around the dangers originating from storing CCS waste deep underground. And the way Dom puts it is, how do you make sure that the champagne cork doesn't come out a few years later?
That's a good question, and maybe it's one I should throw back at you, Rachel, but I won't do that. Yeah.
No chance.
So I think one of the, I'm not a geologist. I do talk to geologists, and they all reassure me that they can do it, of course. I think one of the key things to remember, and the way I think about it, is basically the CO2 does go a long way down. It's a kilometre down, maybe even further. Yeah, and this is into rock formations that have held natural gas under high pressure for millions of years. So I think the issue really, I think, is the cap rock, or at least where you inject your CO2. That's really key. But people have certainly, for example, the Norwegians, they've been doing this for the last 20 years off the Sleipner field. They have been pumping the CO2 back down. There were various tax incentives that were introduced in Norway about 20 years ago to encourage them to do that. And they have been doing that very successfully, and it does stay there. So I think one of the key things here is the geologists have a job to do, and these people have a job to do there, picking the best spots. There are thousands of spots around the world that we can use, so we need to make sure we've got the big ones, the best ones. We have taken a lot of oil and natural gas out of the ground. There are some big holes there that are ready to be filled, but we do need to make sure that the champagne cork stays with its corking. I'm not an expert on that. I'm sure there are other people that could do that, but I am reassured from the people I've talked to that this can be done, and there's been lots of studies on it, so I think it should be fun.
There's another question about earthquakes, but I'm not going to test your geological knowledge that far. I'm sure you'd be glad to hear that. So another difficult name for me to pronounce, I think it's Haiku, asks, is the capture only for CO2, or other greenhouse gases as well?
No, it's only CO2. Yeah. So it's just the reaction of CO2 with that amine that we focus on, or at least with our capture agent that we focus on. There are other greenhouse gases, so N2O, for example, nitrous oxide, and methane, and a lot of fluorocarbons. Actually, things that are used as anaesthetics and stuff like that. They're actually quite serious contributors to global warming. We can only deal with CO2. I think there's been a lot of work over the last 5 or 10 years to really tighten up on methane emissions, but still, I think there's still some work to go there. But we don't do any work on that. We would, of course, capture CO2 if the methane was burnt. Yeah, but beyond that, CO2 is the only thing we really focus on. Yeah.
Okay, thanks. I've got another few questions about other uses of fossil fuels. So one's a bit more of a statement from an anonymous attendee. So even if we move away from fossil fuel power, we're still likely going to use oil products. And then Roger asks, there'll be a CO2 footprint in resourcing materials and plant manufacture of your and any capture process. Do you have a feel for how long in time it pushes back its positive impact? So kind of ongoing need to use fossil fuels in the activities.
Yeah, that's really interesting. I mean, the oil products bit, I mean, this comes down to plastics and all this sort of stuff as well. And there's a huge amount of interest in people trying to find alternative to plastics. Plastics are pretty good at what they do, but of course, then you've got the residual mess afterwards that just stays around forever. I think what will happen is we will find alternatives to plastics that will do the same job. Maybe not quite as good, but that probably doesn't matter. I think plastics are over-engineered for what we need them to do, to be honest. Yeah. We will still have a very small oil industry. Yeah. So, for example, a lot of the chemicals you use to make pharmaceuticals, drugs, we're still going to need those, and most of those are petrochemical based. Yeah. And you can't suddenly find ways to make those from renewable crops or whatever. So we're always going to need some, and there is more oil in the ground than we're ever going to use. So we'll always be taking a little bit off, I think. To talk about the CO2 footprint, we've done a little bit of work on this actually in my research group. So Ollie Stansfield's been looking at it, where we've been looking at the amount of energy, embedded energy in manufacturing of amines, for example, compared to manufacturing of our capture agents. And our capture agents do have a substantially reduced CO2 footprint as far as we can tell, compared with amines. If you think about amines, when they're manufactured, the way you do it is you make ammonia, and that's the Haber process. So you reduce dinitrogen. So and that's a very energy intensive process. It's a huge process. It's done around the world on a very, very large scale, but it's very, very energy intensive. That triple bond between the nitrogen in dinitrogen is very strong, and it takes a lot of energy to break it. And because we haven't got any nitrogen in our molecules, that does actually mean that the production process for our chemical is substantially lower in energy footprint compared with an amine. One of the things that we are doing is looking at ways to obviously recycle the solvent. Because it doesn't degrade as fast as an amine, that means it'll have a much longer lifetime. Because we can also recycle it, but at the end of the life, because it doesn't have nitrogen in, if necessary, we can actually combust it, we can burn it. One of the problems with amines is if you try and burn them, then you have to do it under very carefully controlled conditions, because you get a lot of NOx when you're burning nitrogen-based chemicals. Whereas if we haven't got any nitrogen in there, we don't have that problem. So I think at the end of life disposal, we can actually probably just put it back in say a power station or industrial process, maybe a cement kiln or something like that. Just burn it to actually get some energy back from it. It's not, but we're doing a lot of work now, particularly as we start to scale up our processes, to actually understand the solvent degradation, but also then to look at the recycling. And we do think we can actually recycle pretty much everything within we might lose perhaps 5% of material, something like that. So it's going to be a big focus on what we do, because it is very, very important. So it's a very good point. And one of the key things really is how many CO2 molecules will a molecule of our capture agent capture? Yeah, and we don't know yet, but you know, it is in the hundreds, if not the thousands, if not the tens of thousands of times that it will do the job. So you know, we're pretty optimistic that it will be overall sort of beneficial. We're not going to use more CO2 than we actually capture.
Good to hear. So there's a group of questions. I think David, Catherine and Charlie are all asking around the costs of capturing. So typically, what does it cost to capture a ton of carbon today, and how low do you see those costs going in the future? And then a follow-up from Catherine was, how will industry be forced stroke incentivized, I hope, to use this process?
Okay. Good point. Okay, so cost of capture, that is coming down all the time. So there is a large-scale facility. So, well, I showed you Petronova. There's also one called Boundary Dam up in Canada, and that's typically operating about $60 to $70 per ton of CO2, something like that. One of the issues we have with our process is because we haven't built a great big machine yet. It's hard for us to say exactly what it's cost with a degree of certainty, but we do, because we know our process uses a lot less energy, the solvent's going to last longer, all those sorts of things. We think our process will get down to at least $40 a ton, maybe even 30 with more experience. So it's those sorts of orders of magnitude of capture costs. There are also costs then for transportation and storage. You know, so that's not the base cost, but probably maybe another $30 or $40 per ton to actually get it to where it needs to be, something like that perhaps. To get industry to adopt it, I think it is going to have to be things like carbon pricing, and that has to be agreed all around the world. There's no point in us putting a carbon price in the UK if you don't have a carbon price in China, and you can make things cheap in China or India or whatever. You know, and this is the whole point of the sort of the IPCC, the Intergovernmental Panel on Climate Change, and all the various, and the Paris Agreement, and all those sorts of things, where we've got to get agreement around the world as to how we're going to deal with this and how we can sort of level the playing field, if you like, so that everybody has to think about the same sort of thing, has to take CO2 emissions into account. Everybody has to take the cost of the energy used, the CO2 produced, into account in their products. And it's not a straightforward thing, you know, actually calculating how much embedded CO2 is in a particular product is actually quite complicated. And I think also, you know, that there are other things that you can think of beyond that, you know, just in terms of, instead of just looking at sort of dollars per ton or pounds per ton, you know, what is the environmental impact of that sort of thing? So, you know, one of the things with the moving away from petrochemicals is fine if you can find an alternative, or you don't have to use that product anymore. If you can find I'd say a renewable alternative, that's fine. But you know, we've all seen the problems with palm oil and things like that. That was a nice alternative to diesel. But you know, if we're going to sort of cause chaos in Indonesia with orangutans and things like that, then just because it's natural or renewable doesn't necessarily mean it's going to solve the problem. So we do need to look at all of these things really carefully, and fully understanding the life cycle of all of the products, particularly those that are made on a large scale. I think is going to be really, really important going forward. Brilliant,
thanks. So I'm going to bring you back to chemistry here. A couple of questions, one from Michael and one from Edward. There are several proprietary commercial amines that have been proven low energy consumption, low toxicity and low degradation, but there's still plenty of academic research ongoing in Leeds and elsewhere. What's your view on how much further improvement is really possible? And then Edward was just asking, how does the energy efficiency of C-Capture's solvent process compare with others being developed and researched?
So certainly the amines that have been done on scale, which are the amine blends, for example, the C-Capture chemistry is significantly better than that. So I think they were on the amine blends, which have been pretty much optimized around about the 2.7 gigajoules per ton capture. And actually with amines, because they all operate by a very similar mechanism, there are limitations to how much further you can improve that. There are things that are going on with sort of phase change solvents, or solvents where you You can separate a lot of the water so you don't have to heat things up as much. But still, you still have to put quite a lot of energy in there. So you might get it down to 2.5, maybe even 2 gigajoules per ton if you're lucky. What you can't do though is take away the inherent reactivity of amines with oxygen. So most amines, the vast majority of amines will react with oxygen. So they will degrade over time. They will degrade faster than our solvent. I've lost my train of thought now. So there are some significant advantages. Actually, one of the things that I will say is I don't think necessarily that everybody doing CCS is going to use our solvent. Yeah, there are plenty of plants out there. 2,000 plants. Not everybody is going to use our chemistry. It probably isn't the best chemistry for everything. So not everybody's going to use our technology. So that there will be some amine plants. A lot will depend on the local environment, the local availability. For example, you don't want to be transporting thousands, if not hundreds of thousands of tons of solvent all around the world. So whatever is available locally, I think is also important. So I think there are lots of opportunities for everybody. Yeah, there aren't that many different capture processes available that are done on scale, mainly because it does cost a huge amount of money to scale an amine process up to the sort of thousands of tons scale that you would need. One thing I will say is that there are some fantastic amines that have been developed, but then you look at how they're made and you suddenly realize they're actually pretty complicated to make. And you could probably make a kilo of them, you could probably make a ton. But if you suddenly asked for thousands of tons, then the challenges there are enormous. So it really does depend on the chemistry. MEA is dirt cheap, very easy to make. The Pyrazine is dirt cheap, very easy to make. AMP, aminomethyl propanol, which is another that's very regularly included in amine blends, is actually much more expensive and much more difficult to make. And I think I've seen signs that people are sort of moving away from that one because the scale of what you need is actually starting to kick in. It's fine when you need a ton. It's fine when you need 10 tons. But when you need thousands of tons, then that's when these things really start to hurt.
Brilliant. I'm going to ask you, hopefully, a quick one now. Are there any CO2 capture initiatives in the northeast of England?
In the northeast of England, do you count Drax as the northeast, or do you want to go further up?
I'm assuming not. This is a question from Catherine.
I think around Teesside, there are certainly things happening now. I mean, I'm not sure if people are aware, but part of the government strategy is to have CCS clusters around various parts of the UK, and so Homicide cluster is one of them that will have CCS on there, and the anchor project for that is Drax. But there's also an important Teesside cluster. I think there is BECCS up there. There is hydrogen production as well, which is going to have a lot of CCS on there, because the hydrogen, it's not going to be made by electrolysis, it's going to be made by steam methane reforming or similar process, where you actually produce CO2 as well as the hydrogen, and that CO2 will need to go off storage as well. There are some smaller companies going to be doing BECCS, I think, in Teesside as well. I don't know all the details, but there certainly will be a lot of activity around Teesside, I think. And if you have a look in the industrial decarbonisation strategy, you will see some details of who's involved in the Teesside cluster, because there's quite a few companies involved there.
Thanks a lot for that. I think we probably best leave it there. I hope that I've done your questions justice, and Chris has answered them very well. So thank you so much, Chris, for your presentation. I'll let you say goodbye.
Okay, so thank you everybody for your time, especially those of you who joined us from a long way away, I guess. And it's really nice to get the opportunity to actually present. So thank you very much, and thank you for all the questions as well. Thanks, Rachel.
So just a quick request to everybody else left on the call. You will get a feedback form at the end of this webinar. So if you could give us some feedback, it will help us improve future events. There is one more webinar in this series that you can sign up to if you haven't already, and you can see those details right now on your screen. And thank you for everyone who's taken the time to attend today. It's great to see so many people join the call. So